Yeah, sure. So here's a short outline of the talk for today. So what we'll do is we'll go over the audio IO module, like what was the motivation behind introducing that, a little bit of which is also introduced already by Jia. So then we'll move ahead to like why we choose to implement speech recognition in the first place and which model did we use. Then we'll look into the Jasper model, which is the model that we use. Then we'll see how does the sample that I coded works. And then we'll move on to like into the code of how do you read audio files in OpenCV. Then we'll finish with a short demo of speech recognition where we'll take a short audio file and like transcribe it in English. So the AudioIO module was being proposed because like generally what happens is a video comprises of two parts, a stack of frames, which are the images, and the audio part. And the analysis that we usually do uh, only involves the frames, and we actually waste the data that is in the video in the form of audio signal. So the applications that we use is, for example, our object recognition or like stereo image, like stereo depth estimation, etc. So in all those scenarios, there can be applications which can use audio as well to analyze the data more efficiently. And we are also seeing a lot of systems which are actually using more than one modalities in uh, analyzing the data and giving results. So that was the motivation behind implementing AudioIO module in the first place. So it is being introduced in the video IO module, which is already present. So we can actually read, write audio files and capture the audio stream from microphone as we do for videos currently. It's currently available in OpenCV's 4.5.4 dev branch. If anybody wants to like give it a try, uh, it is not perfect as of right now, so it's only available in Windows, I guess. The last I checked, it was only available in Windows. So why did we choose speech recognition? Because it's an exciting application that uses audio, and also it has state-of-the-art applications available. The state-of-the-art models available has pre-trained models. So NVIDIA provides a pre-trained Onyx model for Jasper, which is an end-to-end CNN speech recognition model. This application actually also serves as a good example for anybody who wants to use audio in their systems using OpenCV. Um, so yeah, we chose speech recognition because of that. Then the model that we used is Jasper. It was the state of the art until recently. So this is the architecture of the model. It only uses convolutional layers and a few other patch norm and dropout layers. So the exact architecture is shown in the left side of this slide. So any Jasper model comprises of a Jasper one pre-processing convolutional layer and three post-processing convolutional layers. And any Jasper BR model also has B subblocks, and each subblock contains each B block, there are B blocks, and each block contains R subblocks. And now each block has this type of an architecture where R subblocks are there. Each subblock has a 1D convolutional layer followed by a batch normalization layer, which is followed by a ReLU layer and then a dropout. It is repeated R times, but in the last layer in a subblock, what happens is we add a residual connection after applying a 1x1 convolution and a batch norm, which essentially takes care of the different number of input and output channels, and then we add those add this input with the output of the batch norm layer here, and then we apply ReLU and dropout, and which is then passed on to the next block. So this essentially is the architecture of Jasper. Then these are the results from the paper, the original paper for Jasper. The model that we used is Jasper DR 10x4 with batch normalization. So this one, it uses ReLU activation, and the output on the data set was 6.15 WER. WER is the metric upon which we test the quality of the model, of the speech recognition model. The data set that it is trained on is actually Libre Speech, which is a very famous data set. Next, how the sample works, this schematic presents that. So we take some raw audio, which is then fed into feature extraction module, which extracts MEL filter bank energy features, which are essentially Fourier transforms of the audio, and then applied some more processing. That is then fed into the Jasper model, which we described here. So the input, the raw audio passes from the audio form to the feature form, then which is then passed into the Jasper model, which outputs sort of a prediction vector, which is then decoded using a CTC language decoding algorithm, which is essentially a fancy name to for an algorithm that removes the duplicate characters in a sentence, which is then finally outputs our recognized text. That is the transcript of the audio that we pass on. So this is how it happens. So like the raw audio is passed, and we get this feature sort of vector with 64 channels. And that is passed into the Jasper model, which outputs prediction vector. Then that is passed into the language decoding algorithm, which gives us the transcript of the given audio. So the issues that we faced while developing this sample were basically major issues, or three issues. There were three issues. The first one was that the NVIDIA model that we had in the Onyx format was trained on half precision. That is, it uses FP16 format to store the weights of the model. So, and the issue is that OpenCV does not support that. The DNN module that we have majorly supports only FP32, which is floating point 32-bit floating point numbers. So what we did was we had to like open the Onyx graph and look into each nodes, and then for each node we had to typecast it to FP32 from FP16. After doing that, we also had to like typecast every parameter of the model. So we typecasted that. After that, the output Onyx file was compatible with OpenCV DNN module, and we could use that. The next issue that we faced was that OpenCV does not actually have any code that can do signal processing for us. So we had to implement that using NumPy. So basically what happens is for any audio analysis, we have to like convert the audio signal into the frequency domain by applying Fourier transforms. The application that we had used STFT, which is short time Fourier transform, followed by MEL frequency bank features multiplied to that. So we had to implement all of that. We implemented firstly actually whatever we implemented was already there in PyTorch. So we based our implementation solely from the PyTorch application and a few Google searches. Then the next issue that we had was that OpenCV Python bindings treat any matrix that we pass from Python to C++ for computation as an image. And it does this weird sort of thing where it wraps the channels, and because of that, the data that we were passing was not correct. So the analysis that was actually happening in the background in C++ was giving weird errors where it was saying that data is incomplete. It was a very notorious issue, and after digging in for like a week, we found out that the issue was actually reported in OpenCV earlier. And the issue was that for any matrix of shape, let's say x comma x comma lesser than 256, it would like wrap it into x comma x. So it would get rid of the last dimension. This was actually fixed after we reported this issue, and actually I also suggested a fix, but later on another fix was implemented. So yeah, for that we also had to fix something in our model, which was that we had to apply a reshape node in our graph, in our model's graph. So we did that, and after that, resolving all those issues, our model was actually good to go. So like that was how I developed the sample. So this is the working of the sample, and these are the issues I faced. Now, the development that is happening in AudioIO, we'll talk about that. So the AudioIO currently is supported in limited backends with limited backends. So this is a sample code which we can use to like read a file and get the audio stream with some specific sampling rate. So if we talk about this code, then it's actually in Python, as you can guess. So just as we capture a video file, we create an object of video capture. So cv.video capture, given a file name to that, the file would be an audio file or a video file here. Then we specify a sampling rate, which is 16,000. Then we specify some parameters. So there are 4 parameters that we're using here. So the first one is cap prop audio stream, which specifies the number of the stream that we want to capture. So like if we have multiple audio streams in a video, so for example, there are videos that have multi-language audios. So those audio streams are actually numbered from 0, 1, 2, 3, 4, and so on. So this audio stream is an integer that specifies that stream. The next parameter is cv.capprop video stream. That actually specifies the number of the stream that we want to capture. Since we do not want to capture the video here, we are passing -1. We can pass 0 to like capture the audio and video simultaneously. Then the next thing is capprop audio data depth, which specifies the 32 floating point number that we want the data type of the stream. The next is audio samples per second, which is this sampling rate that we have specified. that is 16,000 samples per second. Then we open this capture using this and the parameters that we just specified. And then after that, we like in a loop, we capture the audio and then save it in this variable and then convert it into a NumPy array. And then return it from the function. So this is a basic example of how we read audio file in OpenCV audio using OpenCV's AudioIO module. So this is under development right now. So you can actually try this by installing the 4.5.4 dev branch. So like you have to build OpenCV from source here to do that. Next, we have some audio samples that I'll actually would like to show here. I'm not sure if you can hear this audio. Give me a sign if you can. Did you hear that audio?
No, I didn't hear any words.
Okay. Let me...
An American, instead of going in a leisure hour to dance merrily at some place of public resort, as the fellows of his calling continue to do throughout the greater part of Europe, shuts himself up at home to drink.
Yeah, I hear it. Now I can hear it.
Yeah, so this is actually a sample from the LibreSpeech dataset. I have actually two samples here. So first one was this, and other one is that.
She opened the door softly. There sat Mrs. Wilson in the old rocking chair, with one sick, death-like boy lying on her knee, crying without let or pause. But softly, gently, as fearing to disturb the troubled, gasping child, while behind her, old Alice let her fast-dropping tears fall down on the dead body of the other twin, which she was laying out on a board placed on a sort of sofa settee in the corner of the room.
So these are the two samples from the LibreSpeech dataset itself. So what we'll do is I'll run this in this speech recognition sample, and it should give us an output like this. I have also tried earlier. So if I show you the code that we have, this is this file. So this file also specifies how you can acquire the Onyx model, how you can convert it, the issues that I have described earlier. The code that is given here solves those issues. So you can import the Onyx module and then typecast it and then remove some layers and like this produces the Onyx model. Then we have the filter bank features and all that code here. So if I like run this, so I have it in.
Shivanshu, are you sharing something? I can only see your slides.
Okay, you can only share my slides.
Yes.
Okay. So I'm not sharing my whole screen. Just wait a minute. I'll share this.
All right.
You can you see Visual Studio Code?
Yeah.
So the thing that I was sharing is this part. So actually, this is the file that I contributed in the OpenCV repo. This comment specifies how you can acquire the Onyx model. It's shared in this drive folder. And to convert it in the format that this file uses, here is a piece of code. If you don't want to run all this, just download this one, and it is already been done in this. So this specifies all that. The actual code is here. So here is the filter bank features, which calculates the features from raw audio. And then we have a decoder, and then the main code. So what I'll do is I'll run this sample, and it should give us the output in the form of a English sentence that the audio was saying. So I have it. The model. Yes. What's happening? For some reason,
It doesn't work?
it just messed up. Um, so here is this audio. So we're using Python 3, and this is the sample. The input audio file is this, and the model is this one. It takes some time.
So it's a little bit slow.
It's slow because my system is slow. So yeah, here is the output of that. So an American, instead of going in a leisure hour to dance merrily at some place and all that. So this was the audio that we saw earlier. And if I do that for the other audio, again, I'm only using CPU to do that.
You mean the back end of the forward?
Yeah.
Okay.
So like to forward the model, I'm only using a CPU because I don't have a GPU in my system.
Right.
That's why it is slow. So here is the output of that.
It's a little bit longer, and it takes a longer time.
Yeah. That's because. So like it's fairly good, I would say. The samples that I have shown is actually taken from the Libre speeches test dataset, the test split. So the model actually wasn't trained on the test part, I hope. NVIDIA did the training. So yeah, that was it from my end. for the talk. If there are any questions, then we can go ahead with that.
Okay, so just now you mentioned that you mentioned the limited backend. For limited backend, you mean when read the audio file, or you mean the backend of the DNN module?
The backend of the DNN module.
Okay. But I think
so. You can actually.
Yes, go ahead.
Yeah, so I was saying that you can actually specify the backend to do computation by using the backend flag. So the supported backends are here.
Yes.
You can see you can use DNN backend, OpenCL and
yeah, because OpenCV DNN module supports several backends, right?
Yeah. It supports OpenCL, CPU, DNN. It actually depends on the configuration with which you have installed OpenCV.
Yes. Well, Shivanshu, can you give your email address to our audience if they have some questions? Maybe they can write email to you.
Yeah, sure. So I'll write it here only. So it's this one or
okay. All right. So if you have any questions about the AudioIO or about how to do speech recognition using OpenCV DNN, maybe you can write to Shivanshu to get some ideas. So okay, maybe that's all for our for today's webinar. Thank you, Shivanshu. Okay, then thanks for watching. Goodbye.